Good afternoon, everyone, or good morning, wherever you're at. This is Q-PAC's Quick Unpack. This is session 4, and we will be covering acoustics with Mo Afshin, one of our product engineers and sales managers at Q-PAC. So a couple things right at the start, you'll see that our screen has changed a bit. If you look up in the top corner, you will see our marketing@qpac.com email. That email is available if you have any questions about the content that we're covering, any questions about Q-PAC in general, if there's anything you want to know about our Impact Summit, the quick unpacks, whatever it is, please feel free to reach out. We also have down at the bottom of your screen a QR code that will link you to our Impact Summit registration. So our Impact Summit is our summit that we're hosting in October 18th and 19th at our facility in St. Augustine. This is for manufacturers, reps, mechanical contractors, facilities teams, facility owners, and any customers that you feel like you'd want to bring. We're going to open up the factory and host tours. We'll have keynote speakers, demos, everything like that. So please feel free to come down. Registration will be available at that QR code below. This unpack, like we were talking about, we're going to focus on acoustics with Mo. So I will bring him in. If you have any questions, please feel free to post them in the chat. The chat will be manned by either Kurt Thomas or Mark James, two of our engineers and product managers that will be online, able to answer those questions, or I will briefly interrupt Mo and he'll be able to answer them live within the stream. So I will make way for Mo.
Thank you so much, Eddie, for the intro. And thanks. Welcome, everyone, again to our, I think this is our fourth unpack session. Great. I'm going to go to the next one. Yeah, as Eddie said, today we're going to focus on the two subjects. It's by popular demand. We're going to talk about these two. So I'm going to start with vibration balancing. And I think since these two subjects, and vibration balancing and acoustics are pretty related. They come hand in hand. It's a good session to have both of them in one half an hour. So I'm going to focus to get it done in 20 minutes. Hopefully, with the questions, won't exceed that 30 minutes time slot. We are going to offer PDH certification, professional development credits. Of course, these are half an hour sessions, so we'll have to give you half an hour credit, but we are going to do this every month, so it's going to add up. Please, if you're interested to get that certification, send an email to Eddie. Eddie's our marketing guy that sends you emails. If you've blocked him, unblock him. It's not spams. A lot of it is regarding our marketing and education material. So send him an email, and we'll send you a certification on that. I'm going to start talking about vibration balancing, and I'm going to jump into AMCA 204, which is the basis that we use for a lot of the guidelines to first test and also interpret what vibration balancing is required for different applications for fans. And from there, I'm going to go to acoustics. So let's talk about AMCA 204. The latest revision of AMCA 204 came out in 2020. That's where that 20420 comes from. I think there will be another revision coming out soon. These standards normally go through revisions every 3 years. So hopefully we'll get another one and we can take a look. This is a really informative standard. If you have access to it, I really recommend people going through. It's not just talking about the test, it also comes with a lot of guidelines on what kind of balancing and vibration is required for different applications for the fans. A couple of terms before we jump and talk about vibration and balance. Let's talk about balance. It is a characteristic of the fan itself. So if the fan is not running, that fan has a balance. That's just a characteristic of the fan. It's the same as a wheel on your car. So how it's measured, they just see how much of the mass is not in line with the center of rotation of that wheel. And that is reported with a quality of balance of that fan wheel. We're going to talk about that a little bit more. And regarding vibration, that is when the fans run. So when you start your fans and they start turning, you're going to see some vibration in your system. That's basically the vibration is. It is not just a function of the fan wheel itself. It is a function of how that fan wheel is mounted on the motor. It is where the fan is mounted, how the fan is mounted. All of these is going to impact vibration. So it's not just a fan wheel thing. It depends on the system and the application. The first table in AMCA 204 that I'm going to show is just how AMCA categorizes balancing and vibration. If you look at on the last column, it shows it's a few BV. It starts from BV1 to BV5. And what BV stands for is for balancing and vibration. Let me just go to the next slide. So BV stands for balancing and vibration, and AMCA 204 categorizes balancing and vibration to 5 categories. Starts from 1 to 5, and as you go from 1 to 5, the required limit for balancing and vibration of those fans become more stringent. So I'm just going to focus on BV3, start from BV3. That is where we are mostly focused on. That is for commercial HVAC systems. That's most of our products go to. And that is, as you go up to BV4 and BV5, it becomes a little bit more stringent. BV4 would be for larger fans for industrial use, and BV5 would be for more computer chip manufacturing. This is a little bit more critical applications, so they require less vibration. And that's what our focus is going to be. Just let's remember BV3 and let's see what it actually means. The next table is just showing what these categories mean in terms of quality of the impeller balancing grade. So that G is a grade, and it is followed by a number, and that number actually shows the unit of that number is millimeters per second. So that is a metric number. So that 16 means that the quality of balance of that wheel is 16 millimeters per second. As you go down that number, it means there's less and less imbalance in your wheel. So a G 1.0 is a lot more balanced wheel than a G16. And as that corresponds to your balancing and vibration categories, starting from 1 to 5. There's another table that shows your balancing and vibration categories, and that's regarding vibration. So this is the more important table. So this is regarding vibration, not just balance of the wheels. So if you look at this, now we are categorizing fans not just based on the wheel balance grade itself, but also how the wheel and the fan is mounted. So if a fan is mounted rigidly on a pad or on a bulkhead, it would be a different requirement than a fan is flexibly mounted. That means the fan is on a spring or rubber and shear. As you see, there's more allowance when you mount your fan on a spring than when it is rigidly mounted, because that spring is going to dampen some of your vibration. And for Q-PAC fans, we mount our fans rigidly on a bulkhead. So you see a typical fan array over there with 10 fans. That gray sheet metal bulkhead in the background of the fans is what our fans get mounted on. We bolt our fans on that bulkhead and they're bolted rigidly. So we don't use any external vibration and isolation. So we are going to use the left side of that table. So if you look at that, we talked about the BV categories used for commercial applications, recommended for commercial applications. And there you can see that we are limited by 3.8 millimeters per second. Now let's look at what our Q-PAC fans are. We use, our fans come from our suppliers. We use, historically, we've used 3 EC fan manufacturers. And for 3 of them, this is what we get. This is a simple rule for all 3 manufacturers that we've used. Any of our smaller fans, anything below 400 millimeter in diameter, would have a balance quality grade of 6.3 millimeters per second. And for anything larger than 400 millimeters, we have a balance quality grade of 2.5 millimeters per second. The reason for that is it's a rule of thumb. The smaller the fan wheel gets, it's a lot more difficult to balance them. They run at higher speed and they're more difficult to balance them. The larger the fan wheel gets, it is easier to balance them. So they come with less vibration. So if you look at the table again, at a 2.5 millimeter for a rigidly mounted fan, we are at category BV4. And for the smaller fan wheels, we would be somewhere between BV1 and 2. So if vibration is a very critical issue, again, we have to remember that this is a recommendation by AMCA. This is not a code that you have to follow. But if vibration is a critical thing for an application, I do recommend going with larger fan wheel diameters, larger than 400 millimeter. Let's take a look at what Q-PAC fans are, in fact, in sizes. We do have 3 fan models that are below that 400 millimeter size, but all of our other fans are larger than 400. Now, there are some applications that will have to go with smaller fan diameters, especially if you look at that 1700082. That's a fan that does really high static. So there are applications that will have to go with smaller fan wheels, but keep that in mind that, what that quality of balance is going to be for the smaller fan wheels. And I'm going to show just, how this actually works. We have done one of our partners. This is for a job in New York, and they have use a third-party lab to test a fairly large fan array inside of a custom cabinet. So this is a fan array put inside of a custom cabinet with other components, filters, coils, everything, and then tested. So they put an accelerometer on the base rail of that unit, pretty close to the bulkhead, and they tested the vibration. And what we got out of this was pretty interesting results. You can see that RMS value there, that was at 0.008. That's about a tenth of what is reported for the G value of our larger fan wheels. So we were using our larger fan wheels in this one. And it just shows that, that number that is reported by the manufacturers. These are German manufacturers. They're very meticulous and very conservative in the numbers that they publish. So what you are going to see in the field may be different and a lot below what is reported. Another reason why we got lower vibration through this particular system was this is a larger system. As you add weight to your fan section, you are going to anchor down that bulkhead. So you're actually going to reduce your vibration by going sometimes with more number of fans on that bulkhead than just a light fan. That's one of the reasons why a lot of these fans are mounted on really heavy concrete bases. So this also helps. Sometimes a larger fan array does have lower vibration than you see with a lighter fan array. All right, before I move on to acoustics, Eddie, were there any questions?
No questions as of yet.
All right, that's good. But please keep the questions coming so I don't put people to sleep. You have no question, Eddie? You're good?
I've learned everything, Mo. I know it all now.
All right, good. Okay, let's move on to acoustics. Just defining a few terms before talking more about Q-PAC's acoustics. So a couple of terms that you may have heard a lot when it comes to sound. There is sound power. This is what is mostly reported by and published by manufacturers. This is what is tested in the lab, is sound power. And there is sound pressure. Sound power is just like balancing, it's a representative of the total amount of acoustic energy, and it is only dependent on the source. So it doesn't depend how far you are from the source of sound. It doesn't depend where you're putting that source, how close or how far it's from a wall, if it is in the corner. It only shows you the power that comes out of that sound source. It is a very good metric to compare machines and how much sound they create. That's why that is mostly what is reported by a lot of the manufacturers. That's what you will see in many of these schedules. Sound pressure, on the other hand, it depends on how close or far you are from that sound source. It is the amount of pressure that sound will put on a surface. So this is basically what you hear. Again, it depends not only on the source, but also your proximity to that source, where that source is located, and etc. Sound power is what we publish, as like many other manufacturers, and this is a good way of comparing apple to apple. So if you have two systems that you know are going to go to the same box and you know they're going to go to the same location, then you can compare the sound power and see how they compare. There are calculations based on the proximity and the location of the sound system that you can convert the sound power to sound pressure, and that's how a lot of the acoustical consultants do to replicate what the actual sound you're going to hear out of these systems. The other term that you will see are octave bands. So when you hear something, there are a combination of sounds in different frequencies, and to show a better reflect a better way of what that sound is, we are going to show that in different octave bands, in different brackets of frequencies. We show that from 63 hertz going up to 8,000 hertz, and that is the frequencies that human ear can hear. So we're only going to show it where it is possible for humans to hear. Not every octave band is perceived by the same part of your ear. So every different parts of the ear will hear different frequencies. And this is really generalizing, but to human ear, the higher frequencies are mostly perceived less pleasant. So again, it really depends on who finds what not very pleasant, but generally it's the higher frequencies that we find less pleasant. So it's another reason why we do create these octave bands, and we show these we show the sound power in different octave bands. Now let's move on to
quick interruption for you, Mo. We have one question that says we can get 1/3 bands.
No. So what we report is only going to be in these bands. No, that's a quick answer. Yeah.
Okay. And then we have another question, and I'm going to ask, but I did ask for the poster Mel to repost it. So maybe we can ask it at the end when we have our other question, session. But he said DBA 5 feet free field from the inlet.
Is that a question or a comment?
I'm not sure. So maybe that was a poor interruption on my part, everyone, but hopefully Mel will rephrase it and we can ask at the very end. So go ahead and continue, and we'll get that at the end.
You could just get a little bit of clarification there. We'll definitely
sure, absolutely.
Yeah. And let's talk about the sources of sound. The main two sources of sound, again, like vibration, sound really, really depends on your system and on the application. But there are two parts that create the main sound in fans. First would be the motor and how the motor is connected to the fan wheel itself. In EC fans, the motor is extremely compact. So I've put an exploded view of an EC, a typical EC motor, and on the left, you'll see it all together. The fan itself will mount on the external rotor shell. So if you look at the exploded view on the most right component, that's a rotor, the fan will get mounted on that. EC motors actually do not have a shaft. And what turns in an EC motor is that external shell. All of these fans come pre-mounted, pre-assembled, and pre-balanced from the factory. Every single one will get tested before they're shipped to us. So these are all positives and benefits of EC fans. Just because the fan and the motor both come from the same factory, are mounted in the same factory, and that the fan itself is very close to the motor. The motor, if you have seen these fans, the motor sits pretty tight in the back of that fan. The sound that comes out of an EC motor itself is extremely low. We have a demo unit going around these days in some of our offices around the country, and if you get a chance and go and stand by that demo unit, you'll see that the motor itself, it's very hard to hear anything out of that motor. So EC motors compared to the traditional AC induction motors are inherently quiet. Now, the other bigger portion of sound that comes out of fans is the fan wheel itself. So when you turn the fan wheel and you're moving air, that air is going to create some sound, that aerodynamic part of your fan. You're creating pressure, you're pressurizing the air, you're moving the air, is going to change direction, going from the fan wheel itself out of your cabinet. It's going to change direction in the cabinet. That all is going to create some sound. Now that depends on, the type of the fan wheel, if it is an impeller fan, a propeller fan, or if it is a centrifugal fan. The blade design, it really depends on the design of the blade. Today, there are a lot of manufacturers that come up with very novel ideas. They do a lot of work, come up with corrugation on these blades to reduce the sound by, 1 dB. So it's that design of that blade itself, even if it's airfoil for both of two systems, you might get a lot less noise in one airfoil blade than in the other. So that's also important. The material that the blades are made of, right now Q-PAC has fans that are aluminum or fans that are high performance composite. That also changes the acoustics of the system, number of blades, and the speed that the fan runs at. So those are the other things that changes the acoustic of these systems. Go.
Quick question for you. Can we get sound on same fan as it loads and unloads?
So as it loads and unloads, if you're talking about, the fans ramping up, you can run our software and get sound data on all of our fan arrays at different points, but that would be a manual work. So you'll have to run it at, in intervals. For example, if it is, running at 200 RPM, starting from 0, you have to run it at different RPMs to get the sound. But of course, you will get sound data at the design point out of a software.
Thanks, Mo.
All right. A few rules of thumb. Again, rules of thumb means take them with a grain of salt. Sound depends on many things. Not just your fan wheel and not just your motor, but also where everything is located. But in general, when you go to a smaller wheel that runs at higher RPM, that fan is going to generate more sound in the higher frequencies. As I said, but mostly the higher frequency sound is going to be less pleasant to human ear. So keep that in mind. We talked about smaller wheels being a lot more difficult to balance. Now, this is also another fact about smaller wheels. When we're talking about EC fans, and you can see 2 of EC fans down there, the one on the left is an aluminum wheel, the one on the right is high performance composite wheel. If you look at these EC motors, you see the motor sits at the back of the fan. It's really good because now you can balance the fan and the wheel really well. But sometimes these motors become really large that kind of interfere with the airflow that comes out of these wheels, and that changes the sound that comes out of the fan as well. So that we don't want to put a very tiny wheel on a very large motor. Sometimes we don't use them, but there are fans that are called, like their motors are called pancake, and they're really large motors. Those do impact the flow that comes out of these fans. So that also impacts the sound. And the last one is, again, I'm generalizing. This is based on what I have seen myself out of the data that I've looked at. But the lighter the wheel gets, the material that you're using on your wheel, you're going to reduce the sound that comes out of them. So the high performance composite wheels, the ones that come in the color blue, or you see that on the right, they are a slightly lower sound than the aluminum wheels. Now, I cannot say for sure it's because it's high performance composite, but sometimes they're easier to design a weird shape on those blades as well. So it could be other reasons, but that's what I've seen myself in, looking at a lot of data coming out of these fans. So that's another way, another rule of thumb I just wanted to add here. Now I'm looking at 3 systems and how the system, I'm going to make this big because the font is very small. I hope you guys can actually see the numbers that are there. So all of these values are out of our software. When you run, one of the great things about Quips, if you have used it, is that every system will come with sound power data for that fan array at the operating condition. So I ran 3 different fan arrays. This is for 20,000 CFM, running at 4 inches of total static pressure. And I use different fans. The number of fans are the same. It's just going with different fan models. So on the very left, you'll see our largest fan wheel, which is a 560 millimeter diameter with a smaller motor. And I go right to smaller and smaller wheels. As you can see, to create that CFM, to create the flow rate with a smaller wheel, you'll have to run at higher speed. So I start at a 375 RPM going up to over 4,000 RPM on the smaller wheel. And as you can see, that is showing how the sound is generated in that fan system. It really depends on the octave band as well. It's not the same across the board, but you see there is something between 15 to 20 dB difference between my lower sound system to the higher sound system. Again, when selecting a fan array, you're not just looking at one single issue. You're trying to solve, the first thing you have to do is to move air at a CFM at a static pressure. So that's the number one thing you're going to do. Although if your application is a lot more critical with sound, there are different options that you can look at. You can go with larger fan wheel diameters to reduce your sound on your system. So this is a good example to show, there are different options available for when it comes to acoustics. And again, going back to our fan portfolio that we have, I have highlighted the 2 fans that have the largest fan diameter. And those are the ones that actually go up really high CFM, although their static is limited on them. So it's, sometimes they may not work for every application, but they work for some applications that, our static doesn't exceed that 5 inches. And that's what mostly we see, a lot of the times that acoustics becomes very important is when the fan arrays are located in proximity to, residents. If I was working on a job that we were putting fan arrays in each floor of a residential building. We had a mechanical room with a standalone AC that had a compressor inside of that mechanical room, and we had to bring air to cool down that room. So it was an easy decision to go with, you know, the 17888 that is basically our lowest sound fan, and we didn't have a lot of static there, so it was an easy decision to go with that fan type. As you see, again, a lot of our fans, we have a lot of fan options within that 400 to 500 millimeter. So these are all going to be pretty quiet fans that you can pick from. And the last two slides, I did go through a rabbit hole of looking at, you know, yesterday I was reading for 2 hours about human ear and how we hear sounds and what it means that we look at these dBA and decibels on these schedules, and sometimes we don't even know what that means. I didn't know much, like what is good, what is bad, and what makes a difference. A 20 dB is just a table that I came up with. A 20 dB, it actually makes a dramatic change in sound. So when looking back to the table that I had here, see that, you know, this fan array is probably going to be a lot quieter than the other fan array. So we're going to make a difference between these two, as you know, whichever you pick. So again, looking at the options that you have through Q-PAC, you can make selections that are a lot quieter than others, depending on the application and depending on the possibility of picking up these fans. And the last thing I just wanted to mention is, again, going back to humans and how humans hear things. It's you may have heard of A-weighting, the sound emission out of these fans. When you're doing A-weighting, one, you will have to do it based on sound pressure, so that we are dealing with what actually we hear, not the sound power, because the sound power, again, depends on a lot of other things. It depends how far you are from that source. But when you're A-weighting, you will calculate the sound pressure, and then because the higher frequency sound is less pleasant to humans, we add some dB to those, between about 10,000 to 5,000 hertz. And on the lower frequency, we actually take away some dB. That's how the A-weighting works. And that is basically, we're trying to simulate what human ear hears. So if you ever hear an acoustical engineer, an acoustical consultant asking for A-weighted sound data at 3 feet away from the source, then you can come back to us and we can do the A-weighting for you and send you the A-weighted values. That is all of the slides that I have. A little bit of summary. Q-PAC fans, EC fans that we get from our suppliers, come pre-assembled and pre-balanced from factory. It's a huge bonus because the fans, each single fan that comes to Q-PAC and goes out is balanced by factory on the motor itself, not the fan separate from the motor and then put together. Q-PAC fans below 400 millimeter diameter are the balance quality of G6.3. Anything above 400 millimeter, balance quality of G2.5. And then based on this, you can go back to the tables at AMCA 204 and see where you stand. EC motors are inherently quiet motors. When you're designing for critical applications for both vibration and sound, I recommend going with larger fan diameters. We have a lot of options between 450 millimeter to 560 millimeter, so you can pick those ones instead of going to a smaller fan wheel diameter. Again, picking fans depends on a lot of other factors. So when it comes to vibration and sound, there's a lot of different factors that you have to look at. Fan wheel diameter is one of them. It's not the only thing, but that's a good indication of how the system is going to behave. The other ones would be fan material, speed, and basically where that fan array is mounted and how it is mounted. All right, Eddie. Done with my slide.
the moment we've been waiting for. So right up front, I did make sure to comment in both places. We have an integration issue. I think it's a platform issue where when we comment here, it doesn't directly go to LinkedIn. So I'm sorry that I didn't notice some of these that were coming in, but we will address them now, which is great. So it looks like if I scroll up to the top, we have Mel asking noise up by 3 dBA versus single fan.
All right, let me just go up so I can see
Yeah.
as well. So can you repeat that, Eddie? I can't. Okay.
Yep, it says, it's right after the question, can we get sound on the same fan as it loads and unloads? Mel asks, noise up by 3 dBA versus single fan.
I think the question might be about a fan array versus a single fan. Our software, anything that comes out of the software would be based on the fan array itself. So you don't have to worry about a single fan noise. It's anything that comes out of the software would be a fan array sound emitted. So everything is calculated based on the fan array. And you can't say, again, if I'm getting the question right, hopefully I am, you can't just say it's a 3 dBA add for a fan array versus a single fan, because it depends on how many fans are in that fan array. But yeah, there is calculations that we do. So the data that we get, the data that the fan manufacturers test are all single fan. And then for the fan arrays, you'll just do a calculation to get the sound out of that fan array.
Perfect. Next question. Hugh said, perhaps they missed it. All 8 octave bands, question mark?
Yes, you will get data for all 8 octave bands. Correct.
Perfect. Then Hugh asked, partial wheel width or banding, or we get what we get? Question mark.
Yes, so there is no partial wheel width with EC fans. You will get a package. So the fan wheel, the motor, both come together. It is not like the induction motors where you get a motor and a wheel and it comes in partial width. So the answer is correct. You will get what you get.
Perfect.
With fans, yes.
Next question, and I'm not sure quite what it's referring to, so I hope that you do. You're assuming only turbulent flow? Question mark.
Yeah, so the flow that comes out of these fans would be turbulent. So we are assuming turbulent flow coming out of the fans. Now, anything downstream, that depends on the speed. When the flow develops, then that might be turbulent or laminar. I assume in commercial applications, what we're dealing with, that would be mostly turbulent flow. So yes, we are assuming only turbulent flow.
Perfect. And then Mel complimented your presentation, by the way, and said that they are interested in the future on AHP versus BHP, constant system and turbulent flow. So those could be fun things to break down in the future. Hugh said that is the old single to dual edition 3dB add. So
old single to dual edition. Yeah, I'll have to get with Hugh, and maybe I'm missing something, but we'll get together and talk more about that.
Perfect. So if there are any other questions, please submit them. But while you're doing that, I will remind you, we do have those PDH credits. They will be available. Please email me at the email that Kurt provided earlier in the chat, eLegaspi@q-pac.com, or you can email this marketing@q-pac.com. That's on the screen. They both go to me. I'd be happy to get you connected with those PDH credits. Our Q-PAC Summit, October 18th and 19th in St. Augustine. We are inviting manufacturer reps, mechanical contractors, facility teams, and owners, as well as any customers that you'd like to bring in. You can email me at that marketing email, or you can scan this QR code at the bottom of your screen. And our next quick unpack session 5 is hospitals and medical facilities. We will be going through a number of job projects and why Q-PAC does or doesn't make sense in hospitals. That will be Thursday, July 27th at 1:30 p.m. Eastern. That's kind of the standard time, and roughly Wednesdays or Thursdays are usually when we would like to host them and have them at the end of the month. So if we don't have any more questions, we will be wrapping this up. I'll give people about 20 or 30 more seconds. And again, any questions we didn't answer, any information on any events that we're having, anything that you have, please email me at that marketing@q-pac.com. Thanks for joining us, everyone. We had a blast. We'll see you in the future. Bye.